Hi, girls. Sorry I can't make it to class today with the math competition, but I did record myself with this lesson on how to convert polar and rectangular equations how to convert between the two. Okay, so before you get started with this video, I did want to ask you to go ahead on Blackboard and check your homework first from the night before, from yesterday. I did post the answer key on there, so you can check your answers. You can kind of talk them over too with anyone sitting near you or with a partner. Bring questions with you tomorrow, and we can go over them in class together. Okay. For today, I do have a couple of problems for you to try. If you want to write these down. And again, we'll go over those tomorrow before the start of class. Also, a reminder for tomorrow, we do have a quiz coming up on section 6.3, which is your parametric equations section. And for the beginning of 6.4 with what we did yesterday, with converting back and forth between rectangular and polar points, as well as, what else did we do? Plotting points as well, polar coordinate points, and also finding all possible polar coordinates for a particular point. Right. Also, when we come back from our break, the next Tuesday that I do see you, we will take our test. So we'll review that Monday, make sure we're ready to go for that. Okay. All right, so let's get started. So we are now going to be talking about polar and rectangular equations and converting between the two. Okay. So for example, if we have a polar equation, we're going to start out with r equals 4 times the cosine of theta. We're going to go through and use the same formulas that we use to convert points, polar points and rectangular points. We use the same one in order to convert between the equations. Okay. So I'm going to go through kind of step by step for this first one here and kind of explain how we're going to go from our polar form to our actual rectangular form. So like y and x being our equation instead of just r and theta. Okay. So to start out here, we want to try and get this equation into one of these forms here. That's what we're trying to use, so we can kind of simplify and substitute away here. So what I'm going to go through and do first is I'm going to, and this isn't something that I automatically would think to do first off, but what we're going to do is multiply each side of this equation by r. Because now if we multiply each side of this equation by r, we end up with an r squared over here. And if I multiply this side here by r, notice I put in parentheses r times the cosine of theta. Because if you notice from your above formulas here, r times the cosine of theta is all actually equal to x, which I have here. And our r squared, we know, is equal to x squared plus y squared. So what we're going to do next here is just substitute those values in for the r cosine of theta and the r squared. So now we actually have our equation all in terms of x and y, which is a good start. Now we just need to rewrite this into a form, into an equation form that we're familiar with. So what we're going to do, since this term has an x with it, I'm going to subtract it over to the other side. And in this case, what I'm going to do is try to complete the square here. So I'm going to take this middle b term, I'm going to divide it by 2, and then square that. So I know what value to add to both sides of our equation. So I'm going to add 4 here, and I'm going to add 4 here. Because now we just made it so that this trinomial here is a perfect square factor. So we can break it up into x minus 2 times x minus 2, which is x minus 2 times the quantity squared. We're going to keep the y squared here as well, and we still have 4 on the right side here. So now if you notice, we just rewrote this previous equation we had here in the equation form for an actual circle. And if you remember, our circle equation was usually x squared plus y squared equals the radius squared. The only difference with this one is we have a y minus 2 here. So the only thing that changes is where the center of your circle exists on your graph. So here's our x-axis is going to be moved 2 units to the right. Remember, it's inside parentheses here with this x, so it's moving it left and right. And our y value doesn't have any values with it, so that's still at 0. So our center of our circle is 2, 0, and the radius, remember, this is always r squared, so it's going to be a 2. So the nice thing about these types of equations is you can actually check your answers for these in your calculator on the graphing function. So when you go through and try graphing these on your calculator, we're going to need a new form or a new mode for this one. When we go through and actually graph this, we need to make sure that we are in, here it is, polar graphing mode on your calculator. So I brought up my calculator here, and I want to show you, if you go to your mode key, you're going to have to go down here to where function and parametric were before that we used. We're now going to go over to polar, so just highlight that and hit enter. And also, since we have a sign in this function, we're going to need to make sure you're in radian mode. Otherwise, you're going to get a completely different graph, which doesn't make any sense to you. Okay. So now in your calculator, let's go ahead and type in, it was 4 times the cosine of theta. So from the previous example, so 4 cosine, and your theta is your x and t button that we've been using this whole time. Okay, and enter. Okay. So I'm going to set up my window here. Since we said that this thing was a circle, for a window, I'm going to make sure my theta values, just like for t when we're talking about parametric equations, I'm going to make sure these are going from 0 to, and I plugged in 2 pi. My calculator automatically changes that for me. But I went and did that to 2 pi, because usually, like we know, a circle, total units around the circle, we're dealing with from 0 to 2 pi as our angle measures. For my theta step, I just did 0.1 just so I could see every single point along the way. And I just did general x and y values here, -5 to +5, just to kind of get an idea what this looks like. So if I hit graph, you will end up with your circle in this case. Okay. And notice our center of this thing is at 1, 2, 0, exactly like we found in our equation. Right, so let's look at another one, a little bit different of a type of equation that we're working with here. Right, so let's say we have now r equals 4 times the secant of theta. So in order to start with this one, we need to go through and first, let's rewrite secant in terms of cosine, since we know it's the reciprocal function of secant. Okay. So to start out with this, again, using that trig identity, I rewrote this as r equals 4 over cosine of theta. I just put a 1 over this r here, so I can go through and cross multiply this equation. So notice when I cross multiply here, I ended up with r times the cosine of theta equals 4, which remember our r times the cosine of theta is technically equal to x. So our equation actually for this ends up being a vertical line at x equals 4. So again for this, we can go through and check this in our calculator. Let's see, if I go through, I'm going to do 4, and remember we don't have a secant key on our calculator. So we're going to end up doing 4, I'm going to do divided by our cosine of theta. So we need to make sure we do your, and let's see, for this one, I'm going to graph this to see what this looks like. Yep. And we actually do end up with a line, a vertical line, that's just intersecting at x equals positive 4. So we looked at how we can go between polar equations to our rectangular equations. Let's break this up, and now let's go from, that was our graph we just looked at. Let's go now from a rectangular equation to a polar equation. So for this particular type of problem, again, we're going to want to start by multiplying everything out here. Because eventually we want to get to use one of these equations, or a combination of these equations, to help us to get all of this from x's to y's to r's and thetas. Okay? So I'm going to start out by multiplying all of this out, expanding it. So multiply it out by two binomials, and then I tried to combine like terms here. So notice with our values on the left, the actual constants, they actually eliminate each other out. And I went through and rewrote this left side of the equation to end up with the x squared plus y squared. Because we know from our formulas up here that x squared plus y squared is actually your r squared function. So since that's r squared, I'm going to replace that with r squared next. Remember, x, we know, is r cosine of theta. So we're going to plug that value in here, And then for the y, we're going to plug in r times the sine of theta here. Okay. So, and again, that's just plugging in these particular functions we have from above, the equations. So now from here, if you notice, all three of these terms all have an r in common. So let's factor it out. So if we go through and factor this out, now we can go through and use your zero product property, set each of these factors equal to 0. So if we set this equal to 0, it really just gives us r equals 0, which is really just 1 point at the origin. It doesn't give us a whole lot of information about this actual equation. But if we set this whole thing equal to 0, I went through and actually added 6 cosine of theta and your 4 sine of theta over to the other side of the equation to get this in our r equals form. And this is actually our polar form equation. It only has r's and thetas in it, with our sines and cosines. So right now, I want to give you 2 of these to try, 1 of each. So at this point in the video, pause it, try this example, or try this problem. When you have completed this problem, go ahead and hit the play button again to check your answer. So for this problem, it's very similar to the first problem that we looked at. So we want to go through, multiply r on each side, r times r, and r squared equals x squared plus y squared. The r sine of theta ends up equaling y. Going through, now we are adding this over to the other side. Right, so to continue with this problem now, I had to change that to a plus sign there for a second. But if we go through, and now we are going to complete the square with the y's instead for this problem, since this had a y in it. So we take that b value, divide it by 2, square it, add that to both sides. And then we have this set up with the y terms to be factored into a perfect square binomial. So then from here, we end up with your circle, again, your circle equation, with our x value being 0 for our center. This case, it ends up being the opposite, so negative 3 over 2. And our radius ends up being, again, the square root of this, which is 3 over 2. For your second example, go ahead and try this problem. Again, pause the video. When you're finished, unpause the video and check your answer. To go through this one, notice this has x and y in it already. There were no x squareds or anything like that. So we can just go through and plug in your r cosine theta, and for y, your r sine of theta. And again, if I factor out an r here, Getting r by itself is as simple as dividing both of these sides by 2 cosine of theta minus 3 sine of theta. And in this case, we end up with your final solution. Right, so I did also want to show you a application of using these polar coordinates and how it's going to use in the real world. The main reason for this is dealing with radar. So like in, say, submarines or in airplanes, they're able to use radar to determine how far certain planes are from each other or how far certain ships are from each other. So just to give you an idea of this, it says we have radar that's detecting 2 airplanes at the same altitude, so they're at the same exact height. Their polar coordinates are 8 miles at 110 degrees and 5 miles at 15 degrees. So they actually gave you a sketch of this so you could see. So as far as the 2 planes flying at the same altitude, think of this as a like sky view for your radar here. We're looking all the way up and looking down at the airplanes here. So in this case here, this particular airplane's that is detected, it's telling you from this actual pole, this is a unit of 8, and it's 110 degrees from the polar axis, the x-axis. Whereas this here is 5 units away from the polar axis, or from the polar pole, and it's 15 degrees from the polar axis. So, in each of these cases, you know this length is 5, you know this length is 8. What we're looking for is how far apart are the airplanes from each other. So we're actually looking for this distance here in between them. So what I went through, I graphed what we knew so far. So we said the 8 and the 5 are the lengths of these 2 sides, and we're looking for the distance between them, this distance here. So what we can do is look at this as a triangle. If we know this is not 5 degrees, it was 15 degrees, and if we know this entire angle here was 110 degrees, we know this angle here of the triangle is only 95 degrees by subtracting the 2 from each other. So in order to solve this problem for the distance, you have to think back to last unit, to the method that you had for solving for a distance giving 2 sides and the included angle in this triangle. Again, it's not a right triangle, so we can't use regular SOHCAHTOA. So hopefully you are thinking the same thing I am. We need to use your law of cosines. So this distance here is equal to the 2 sides that were given squared added together minus 2 times those 2 sides multiplied together times the cosine of the angle in between. So that was what d squared was equal to, so I took the square root of both sides and actually plugged all of that into my calculator, and they are about 9.8 miles away from each other. So now that we've gone through these types of problems together, I'd like you to go ahead and take some time to try your homework problems for the rest of the class period. Bring them with you tomorrow. We will review them before we take our quiz to see if we have any questions on anything. All right, have a great day, girls. Bye.